Our ability to communicate information into and out of integrated circuits is increasingly a bottleneck in all forms of computation and communication. To go beyond the 112 gigabit per second links currently under development, we need to re-examine everything in our interconnect fabrics and seek new paradigms. In this talk, I'll describe our work at the University of Toronto on techniques to allow the transceivers for our chip-to-chip interconnect to intelligently coordinate and co-optimize their performance and power consumption. Modern infrastructure and enterprise equipment includes a wide diversity of links between chips. Links targeting data rates exceeding 100 gigabits per second between large ASICs can exhibit up to 8 dB of loss at one-half the baud rate due to each ASIC package alone. Thus, links between closely spaced chips may exhibit, say, around 18 dB of loss, with perhaps a millivolt of crosstalk and other noise. Other links may traverse connectors and long lossy printed circuit board traces, resulting in over 30 dB loss and much higher crosstalk. However, recently published research has confirmed that most links in a typical system will exhibit loss and crosstalk between these two extremes. Due to variations in equipment design, the current paradigm is to design transmitter and receiver circuits to operate robustly over worst-case channels, especially since the precise loss characteristics of each link is unlikely to be specified when the ASICs are designed. This results in significant over-design for most links. With I/O transceivers occupying a large and growing fraction of overall ASIC power and area, such over-design will be intolerable at next-generation data rates. Part of the solution to the I/O bottleneck is likely to come from completely new interconnect paradigms. The hope is that these new forms of interconnect can alter this histogram in future systems. Long links can be converted into optical links to obviate the need for ever more expensive equalization, modulation, and coding. At the other extreme, systems may be reimagined so that neighboring dies are co-packaged and communicate via dense, ultra-short-reach interconnect, permitting low power consumption at high aggregate throughputs. The role of these new paradigms will depend on research progress, lowering the cost and power consumption of the associated transceiver circuits and packaging technologies. Our lab is conducting research in both of these directions. Shown here is an example of a USR link we published in 2016 comprising 20 gigabit per second transceiver circuits on two 28nm CMOS dies bonded to a passive silicon interposer with single-ended interconnect. The use of a silicon interposer ensured matched coefficients of thermal expansion, allowing for a relatively dense 95 micrometer I/O pitch. Routing on the interposer was arranged on a 10 micron pitch. The bandwidth density of 825 gigabit per second per millimeter squared was achieved on each die, and 2 terabits per second per millimeter squared of bus width on the interposer. In spite of the high bandwidth density and single-ended signaling, negligible crosstalk was observed in measurements. In order for optical interconnect to be used for more long-reach chip-to-chip links, low cost and a high level of integration will be required. The transceiver's front-end circuits, transimpedance amplifiers, and transmit drivers, traditionally implemented in SiGe by CMOS technologies, should ideally be integrated into nanoscale CMOS alongside high-speed SerDes logic, forward error correction, signal processing, and other computational logic. Our past work in this area focused on equalization and switched capacitor techniques that are well suited to implementation in nanoscale CMOS and can be used to overcome CMOS's shortcomings compared to SiGe by CMOS and optical transceivers. Here are two prototype demonstrations in a 28nm CMOS technology operating at data rates up to 40 gigabits per second. Whether or not these new paradigms play a large role in the future, it's clear that increasingly the interconnect fabric inside high-end computing and communication equipment is highly heterogeneous. Some links will be short and others long, some noisy, others less so. And it's also clear that overdesign will be intolerable given power and cost constraints. But instead of transceivers designed to meet fixed, worst-case specifications, imagine that all transceivers autonomously and continuously co-optimize their performance. That is, imagine they are able to coordinate their equalization, termination, swing, and other parameters. Imagine transceivers designed with enough flexibility to allow for different modulation formats and forward error correction codes. Imagine all these parameters being intelligently and dynamically adjusted to meet instantaneous performance demands with minimal power consumption. In other wireless and DSL applications, fixed data rates are not guaranteed because performance demands and channel conditions vary so much. Why not take a similar approach to interconnect? Now extend the idea to an entire data center where all transceivers are tailored to the typical, most common operating conditions. All links are reconfigurable to operate at the lowest possible power consumption necessary to maintain their performance. We have high bandwidth links where they're required, and low bandwidth elsewhere. Unneeded links are powered down. That's the vision we're pursuing. I'll now share 4 of our projects moving us toward this vision. There is of course already lots of effort on power scaling SerDes transceivers for varying channel conditions. The problem is that the entire architecture is generally geared around optimizing the power and performance for the relatively few worst-case channels. The resulting power-hungry transceiver circuits in DSP can be power scaled for lower loss or lower noise channels, but the power savings are typically modest, say 20% power savings for typical channels increasing up to around 30% power savings for the best-case channels. I've indicated some energy efficiency numbers here that are representative of modern links. Clearly, a better approach, if possible, would be to tailor the solution to the typical conditions which arise in practice most often. Obviously, the worst-case channels still need to be dealt with somehow. Perhaps the system could tolerate lower throughput on those few links, so long as the overall system performance met instantaneous demands. If not, since those channels arise relatively infrequently, some extra power consumption may be tolerable for those few links. For example, they could employ more powerful FEC, or repeaters, perhaps optical repeaters. Overall, the system power and cost would likely still benefit from the lower average power consumption. In this project, we demonstrated a receiver with a self-optimizing, non-uniform quantizing front end. Specifically, the front end includes an ADC with maximum 6-bit resolution suitable for 4PAM links over channels exhibiting up to approximately 30 dB loss. We made it possible to dynamically adjust the resolution of the ADC by deactivating quantization levels that were not benefiting the system's overall performance, and to save power by doing so. Using a combination of greedy search and LMS adaptation algorithms, the ADC quantization levels and digital equalization parameters were dynamically co-optimized. For example, shown here is a simulation of the optimized quantization levels. You'll notice that they're highly non-uniform. More accurate quantization is performed in signal ranges that occur more often. Here's the prototype implemented in a 16nm FinFET technology and used to establish a 64 gigabit per second 4PAM link. The use of dynamic comparator circuits in the ADC allowed for aggressive power savings in low-loss channels. The optimization maintained a fixed bit error rate target and afforded 65% power savings over channels ranging from 30 dB to 9 dB loss at 16 GHz, one-half the baud rate. The work was presented at the International Solid-State Circuits Conference in 2018. The following year at ISSCC, I participated in a project further along these lines, where an evolutionary algorithm was employed to select the best among over 10 million analog front-end settings. The optimization takes place in an embedded processor in less than 1 second. Future transceivers will require advanced optimization of even more parameters to ensure we're achieving the very best possible combination of power and performance for each link. Having described this first project on non-uniform quantizing front ends, I'll next describe our work on 3 other aspects of modern chip-to-chip links. References to further details on each are included in the presentation slides. I'll turn next to techniques that rapidly and accurately model post-FEC bit error rate performance. Wireline links are commonly specified using the FEC limit paradigm. That is, we assume a specified pre-FEC bit error rate target will guarantee a specific post-FEC bit error rate based on the FEC code. We likely take some extra margin to account for the possibility of burst errors. But this approach is naive as illustrated by this plot, where pre-FEC bit error rate appears on the abscissa and post-FEC bit error rate on the ordinate. Note that the same pre-FEC bit error rate can result in radically different post-FEC bit error rates. For example, the purple and green lines consider different channels and equalizers, but the same Reed-Solomon code. And we see that a pre-FEC bit error rate of 10 to the minus 4 may result in a post-FEC bit error rate of either 10 to the minus 18, which is great, or 10 to the minus 11, which is likely inadequate. In this case, the difference arises because the decision feedback equalizer in case A is causing errors to arise in bursts. So even though there are the same number of average errors in each case, they arise in bursts which are more likely to break this FEC code. Unfortunately, it's notoriously difficult to predict when this will occur, and the probabilities of interest are so low that the simulations would be impossibly long. As a result, transceivers are significantly over or under designed using the FEC limit paradigm. We developed a statistical Markov-based model of post-FEC bit error rate, including decision feedback equalizer burst errors and other important noise sources. It allows for prediction of post-FEC bit error rates all the way down to 10 to the minus 18 or lower in a fixed time. We're talking about minutes on a simple desktop computer. The only way to validate these low probabilities is on a high-speed link with forward error correction in the lab. We were able to do so using a 7nm 4PAM transceiver with standard Reed-Solomon codes, confirming the accuracy of our model. In the next project, we sought a mechanism that would allow physical layer transceivers to communicate with each other without interrupting or hurting the integrity of the high-speed data traffic. Such a side channel is needed for transceivers to coordinate and co-optimize their performance. Our method recognizes that receiver clock and data recovery circuits can track variations in TX clock frequency so long as they respect certain limits that depend on the CDR loop parameters. These limits are derived based on this linearized model of conventional clock and data recovery loops. We showed that if a transmitter's clock is modulated within these limits, high-speed signal integrity is not impaired. We therefore modulate the transmitter clock with our low-speed side channel data. The data appears at the receiver in the integral path of the clock and data recovery loop. Shown here is a measurement of this side channel communication on a real 4PAM 60 gigabit per second transceiver. Such a side channel allows physical layer transceivers to communicate and co-optimize their parameters with no overhead or signal integrity impact. Here's an illustration of the experimental setup for the proof of concept demonstration. These are bathtub measurements where bit error rate is plotted against the receiver's clock phase. We see the opening of the bathtub is unaffected so long as the frequency modulation is maintained below 200 parts per million, in agreement with our analytical model. You can review the results in more detail in our recent publication in solid-state circuits letters.
Finally, with 4PAM 112 gigabit per second links currently under development, we need to look for solutions capable of even higher data rates. 4PAM signals require precise equalization, often including decision feedback equalization entailing high-speed, highly parallelized DSP. In many other communication applications, when severe bandwidth limitations are encountered, discrete multitone or OFDM modulation are employed. DMT is therefore attracting research interest for future chip-to-chip links. DMT subdivides the channel bandwidth into narrow subchannels. Each subchannel carries a sequence of QAM symbols, and an approximately constant attenuation and phase rotation is observed within each narrow subchannel. Thus, channel losses can be compensated for with one complex valued multiplication for each subchannel. DMT modulation opens the door to many interesting possible future directions. For example, it permits very fine-grained optimization of links with tremendous flexibility in how bits and available signal swing are allocated to each subchannel. DMT transceivers modulate and demodulate the subchannels digitally, taking advantage of fast Fourier transforms. Among the likely challenges to be faced is the large peak-to-average power ratio DMT waveforms exhibit compared to PAM. This is less of a problem in links where average transmit power is constrained, but in CMOS transceivers, peak signal swings are often limited by low supply voltages, so peak signal swings are strictly constrained. Our models indicate this will necessitate higher resolution in the analog front-end circuits, particularly the digital-to-analog converters and transmitters, perhaps 7 to 8 bits of resolution, as compared with the 6-bit D-to-A converters typical of many 4PAM transmitters. Our results so far suggest that if these requirements are met, 200 gigabit per second DMT links may be achievable over the channels currently under consideration for 100 gigabit per second links. We're characterizing such links in our lab using a combination of test equipment and software. Here's an example where we established a link having 128 subchannels at a sampling rate of 50 gigasamples per second. Pilot signals were simultaneously transmitted on all subchannels, allowing the receiver to infer the loss and SNR of each subchannel. This information is then used to optimize the allocation of bits among subchannels. 32 and 64 QAM modulation is employed on lower frequency subchannels, while simple QPSK or BPSK used in the high frequency subchannels. We intend to use this lab platform to validate our modeling and evaluate the potential for DMT in future chip-to-chip links. In summary, our existing paradigms and transceiver technologies appear ill-suited to go beyond the current 112 gigabit per second links under development. We will have to look beyond the rigidly defined data rate standards and worst-case transceiver specifications that are now commonplace. Instead, we must be open-minded to consider new paradigms, including our use of new types of interconnect, such as USR and optical, new modulation, and new coding. Transceivers should be optimized for the typical, most frequently occurring channels and designed for reconfigurability. Doing so will allow for dynamic co-optimization of all transceivers, which will keep overall power consumption low. At the University of Toronto, we're excited about the research opportunities. Thanks very much for your attention.
So thanks everyone again for attending. I'm afraid that we don't have much time for questions and didn't get too many questions in the chat window, but I'm not difficult to find online. I'm at the University of Toronto. So feel free to follow up with me if you had any interest in anything you heard about today, and I hope to hear from many of you. Thanks again, everyone.